Hello friends, I am Janaki Ghosh and welcome to my video series on exploring mathematics using spreadsheets. In every session of this series, I'll be exploring an interesting aspect or a concept in mathematics. Today we'll be looking at the Fibonacci numbers. You must have heard of the Fibonacci numbers. What are these Fibonacci numbers? Well, for one, they do occur in nature. The number of the seeds on the spirals of florets of a sunflower are Fibonacci numbers. If you look at the clockwise and the anti-clockwise spirals along a pine cone, they are also Fibonacci numbers. The Nautilus shell is shaped like a Fibonacci spiral. The Fibonacci puzzle was actually posed by Leonardo of Pisa, also known as Leonardo Pisano, in his book Liber Abaci. In fact, the Fibonacci puzzle is where we say that the sequence emerged from. So this considers the growth of an idealized rabbit population, and thus goes the puzzle. A newly born pair of rabbits, a male-female pair, are put in the field and are able to mate at the age of 1 month, so that at the end of the second month, the female can produce a pair of rabbits. Rabbits never die, and a mating pair always produces a new pair every month from the second month on. So how many pairs will there be in 1 year? At this point, I would urge you to pause this video and try to analyze this problem for yourself. Now let us see. On the left hand side, we have marked the months, which starts from 0 onwards. And on the right hand side, we are indicating the number of pairs of rabbits in the field. To begin with, in month 0, there is only one male-female pair, that is the black pair. At the end of 1 month, or the first month, they are able to mate. And by the end of the second month, this pair is going to produce this new pair of rabbits indicated by this purple pair. So by the end of the second month, there are 2 pairs of rabbits. Now let us see at what happens at the end of the third month. We already have the original black pair and the new purple pair. And the black pair is going to produce yet another new pair, which is now the red pair. So by the end of the third month, we have 3 pairs of rabbits. Can you now analyze for yourself what will happen at the end of the fourth month? We already have these 3 pairs of rabbits, but the black pair is going to produce yet another pair indicated by the blue pair here, and the purple pair is going to produce a new pair again. So now we have 5 pairs of rabbits at the end of the fourth month. And now I leave you to analyze how at the end of the fifth month there will in fact be 8 pairs of rabbits. So these are the Fibonacci numbers, and in fact this is the Fibonacci sequence, which is 1, 1, 2, 3, 5, 8. And as you may have realized perhaps, that every number is the sum of the previous 2 numbers. So the Fibonacci sequence is said to be generated by selecting 2 initial values, say 1 and 1, and we add them to get the third term of the sequence. Every subsequent term is obtained by adding the previous 2 terms. And thus the sequence goes as follows: 1, 1, 2, 3, 5, 8, 13, 21, and so on. This is a numerical representation of the sequence. But if we had to write it in the form of a recursive formula, then we would write it as f0 is equal to 0, where f stands for Fibonacci number. f1, the first Fibonacci number, is 1, and the nth Fibonacci number will be the sum of the previous 2 Fibonacci numbers, and therefore is equal to f of n minus 1 plus f of n minus 2, and this is true for n greater than 1. Now I bring you to a very interesting sequence. Have you ever seen anything like this before? This is a sequence of what is known as continued fractions. These are indeed very interesting, and the great mathematician Srinivas Ramanujan is said to have done a lot of important work using continued fractions. Now, how do we predict the next term of this sequence? Note that every term, so from the second term the first term is 1, the second term is 1 plus 1 upon 1, the third term is 1 plus 1 upon the previous term. And so if we follow this pattern, the next term is likely to be this, where we write 1 plus 1 upon the previous term, which is this whole thing. So whatever is in the circle here is actually this previous term. And this is a very interesting sequence. But what link does it have to Fibonacci numbers? We will see later. in this video. Now I would like to open a spreadsheet. In this case, we'll be using Excel and generate the Fibonacci sequence and do some interesting explorations with it. And the steps of exploration are actually mentioned on these slides. So I'm going to minimize this here and pull out an Excel workbook. So first I would like to create actually a sequence of the Fibonacci sequence, the first 40 terms of the sequence. So first I will, in column A, input just a serial number, but I'll just put input 1. In the next cell I'm going to just add 1 to the previous number, and dragging this down to 41 is going to give me the first 40 natural numbers. Now we come to generating the Fibonacci sequence in column B. So I'm going to enter 1 and 1. These are the first two Fibonacci numbers. And in the third cell, I'm going to enter B3 plus B2, that is the sum of the first two cells. Once the formula is input, Excel can very quickly compute the Fibonacci sequence. Very interesting, isn't it? So now we can see that the sequence is growing pretty fast, and as you saw that we had seen that 1, 1, 2, 3, 5, 8, but we have 13, 21, 34 and so on, and by the time we reach 18 we have 2584. Now I'd like you to make a guess here. Can you guess how many digits will be there in the 40th Fibonacci number? Well, I would really like you to make a guess here. And let us go down and actually see. So if we scroll down, we see that the 40th Fibonacci number is fairly big and it has 9 digits. Well, now we're going to do some further exploration, and in this column C, I'm going to compute the ratios of successive terms of the Fibonacci sequence, which means in the given cell C3, I'm going to input the formula 1 plus 1, which is B3 plus, I'm going to input B3 upon B2. So when I double click in this corner of the cell, I actually managed to compute the ratios of all the successive terms. So why do we have 1.5 here? That is because it is 3 upon 2, and so on. I have the sequence of ratios of successive terms of the Fibonacci sequence. But you will observe something very interesting. After the initial variations, it seems to steady out to a certain value. And by the time you reach 24, if you look up to, let's say about 8 or 9 decimal places, it steadies out here. So I'm going to give it a different color just to bring it to your notice. And thereafter the ratio remains the same. So it seems to steady out by the 24th term up to about 9 digits of decimal places. Interesting, isn't it? Why does this happen? And would this number, the one that I've indicated in red, would this change if I change the initial 2 terms of the Fibonacci sequence? What do you think? Can you make a guess? Well, let us give it a try. Suppose I change the first 2 numbers to 2 and 5, let us say. Notice that all the terms have been changed, but every term still remains to be a sum of the previous 2 terms. And let us look at what happens to this sequence. Interesting. This ratio still remains the same. Now let me try with another pair of numbers. And this time I'll take the first number to be, let's say, 16, and the second number to be, say, 7. And let's see what happens now. Well, as you may have expected, there is no change in this ratio at all. So this interesting number is often referred to as phi, or the golden ratio. And irrespective of what we have in the first two places of the sequence, the ratio would always steady out to 1.618 up to 3 decimal places. Later we will see why this happens, but for now I'm going to come back to my original Fibonacci sequence. Now in the column D, the fourth column of my Excel book, I'm now going to enter the formula where I'm going to explore the ratios of successive terms of the Fibonacci sequence but with gaps of 1. So I'm going to say equal to this cell, which is B4/B2. And when I double click on this, I get ratios of terms. So it will be like 2/1, 3/1, 5/2, 8/3, and so on. And let us see what happens to this sequence. You will be quite intrigued to know that this also steadies out at a certain value. And that value is 2.618 and so on, which is exactly one more than the golden ratio. This is very interesting, isn't it? And if you compute the square of this number here, it will also be equal to 2.618. So there are numerous explorations we can do with the Fibonacci sequence, but for now I would like to select this and show you what the graph looks like. And I go to the chart option and we find a fairly fast growing sequence which really grows very rapidly later on. So this is the graph of the Fibonacci sequence, and if I delete this now, I'm going to now look at the ratios of the successive terms, and maybe I'm going to look at both these columns and draw a graph. And you will find that the ratios of successive terms steadies out to this blue graph steadies out to roughly 1.618, which is the golden ratio, and the ratios of successive terms with gaps of 1 steadies out to 2.618, which is one more than the golden ratio. So using this, we can do some interesting explorations. And now I would like to come back to my PowerPoint presentation. Okay, so now why does that happen? You notice that in the golden ratio, the terms steadied out, the ratios of successive terms steadied out to 1.618. So where did this really come from? So let me now explain you how this works. So for some value of n, we found that f of n plus 1 upon fn is equal to fn upon fn minus 1. Since the ratios have steadied, the ratio of the n plus 1th Fibonacci number upon the nth Fibonacci number is equal to the ratio of the nth Fibonacci number upon the n minus 1th Fibonacci number. And suppose this is equal to, so let this be equal to x. Now we know that f of n plus 1, according to the definition of the Fibonacci sequence, is actually fn plus fn minus 1. Alright. Now we simplify this further and write this as 1 plus fn minus 1 upon fn is equal to fn upon fn minus 1, and this we took to be x. So in terms of x, this becomes 1 plus 1 upon x is equal to x. If we simplify this, this becomes x squared minus x minus 1 equal to 0. And it's a well familiar quadratic equation. We know that the formula for the quadratic equation, that x is equal to minus b plus minus root b squared minus 4ac upon 2a, where a is the coefficient of the x squared term, b is the coefficient of x term, and c is the constant. Substituting these values, we will get 1 plus minus root 5 upon 2. You can see this for yourself. But x being a ratio, I'm going to ignore the one with the minus sign, and I'm going to take x to be 1 plus root 5 upon 2, which is approximately equal to 1.618 up to 3 decimal places. So this is the derivation of how we arrive at 1.618. Well, then other explorations which can be done nicely with using Fibonacci numbers. So one is the example of the Fibonacci rectangles. So here we see that if we place a unit square and then another unit square next to it, I get a rectangle of side length 2 and width 1 unit. On the length of the rectangle, I draw a square of length 2. So this process is continued, and so let me try and draw it here. So I have a unit square. I place another unit square next to it. So I have a rectangle whose length is 2 and width is 1. Now I draw a square of length 2 units. So now I get a rectangle of length 3 and width 2. And on this side, I place a square of 3 units. And this process continues. So the ratio of the length and the width of the rectangles as you extend this is going to approach 1.618 or the golden ratio. And you can also utilize the Fibonacci rectangles to draw a spiral. So for example, if I take my compass point here and draw a quarter circle inside this and then inside this square, and I take my compass point here and draw a quarter circle here, then take my compass point here and draw a quarter circle here, shifting my compass point conveniently at within every square and taking the length of the square, the side of the square to be the radius, I can draw a quarter circle and continue this process, and we would arrive at the Fibonacci spiral. So some interesting explorations are awaiting you here as well. Now we come back to this sequence. I had promised you that I will come back to the continued fractions because they do have some link with the Fibonacci sequence. Let's see how. So when you compute the values of these terms, what do you get? Well, the very first term of this sequence is 1. As you can see here, the second term works out to be 2, but what happens to the third term? The third term is actually 1 plus 1 upon 2, which is 3 by 2. The next term is 1 plus 1 upon the previous term, which was 3 by 2, so it becomes 1 plus 2 by 3, which is 5 by 3. And this continues. What is so special about this sequence? Well, you have already encountered this in the earlier, and these were the ratios of the successive terms of the Fibonacci sequence. And in every term, both the numerator and denominator themselves are Fibonacci numbers. So can you guess what will be the next fraction? Well, it will be 13 plus 8, which is 21 upon 13. And the next one will be 21 plus 13, which is 34 upon 21, and so on. Ultimately, this goes to the golden ratio, which is denoted by the symbol phi or phi, and this is 1 plus root 5 upon 2, which is approximately equal to 1.618 up to 3 decimal places. Well, the golden ratio is also referred to as the divine proportion, and many artists, painters used to use the golden ratio in their paintings. This one is a picture of the Last Supper by Leonardo da Vinci, who had used extensively the concept of the golden rectangles in his painting. Many well-known monuments also have used the golden ratio in their construction. It is said the facade of the Parthenon in Greece, or the Church of Notre Dame and the Taj Mahal. If you look closely at the construction and their facades, you would find the golden ratio in some form. So, quick recap. In this video session, we have explored the Fibonacci sequence, which is 1, 1, 2, 3, 5, 8, 13, and 21. One of the legends is that it arose from the Fibonacci puzzle given by Leonardo of Pisa, or Leonardo Fibonacci. The ratio of successive terms of this Fibonacci sequence approaches the golden ratio, which is 1 plus root 5 upon 2, which is also known as the divine proportion. But you've seen that the Fibonacci sequence is actually a recursive sequence. So to get any new term of the sequence, you have to add the previous two terms. But wouldn't it be nice if you had a formula which gave you any Fibonacci number? Well, there is such a formula, and this is the last point on the slide, shows that fn is equal to 1 plus root 5 into this term in the bracket. So suppose you wanted to find out the third Fibonacci number, you would just put n as 3 in this formula and you would get the third Fibonacci number. Well, why don't you give it a try? For further reading, you may explore various resources on the internet. I have mentioned these two specific readings. In the second article, you will actually find a detailed derivation of the nth term of the Fibonacci sequence. So I do hope you have enjoyed this video session, and I look forward to meeting you again on my next video session. Thank you very much.